So in last lecture I have taught the 4 points of how to draw the root locus. Now we will see the other points to draw the root locus. The 5th point is those parts of real axis right to which total number of poles and zeros are in odd number are also part of root locus. That means, let us understand this point by taking one example. In last class I have taken the open loop transfer function as gs multiplied by hs equal to k into s minus 1 divided by s into s minus 2 multiplied by s minus 1 plus j1 multiplied by s minus 1 minus j1. So here open loop poles are s equal to 0, 2, 1 plus j1 and 1 minus j1, and open loop zeros are s equal to 1. So I have plotted these, I have denoted these open loop poles and zeros on S plane. So I have generally we denote the poles by a small cross and 0 by a small circle. So here the poles are at 0, s equal to 0, s equal to 2, s equal to 1 plus j1, s equal to 1 minus j1, and 0 is at s equal to 1. So here I have denoted it by a small circle. Now the whole real part is get divided into 4 parts. One from 2 to infinity, another part is from 1 to 2, another part is from 0 to 1, and the last part is from 0 to minus infinity. Now what we see? We see what we see about this part. How many number of poles and zeros are right to this part. So right to this part, the total number of poles and zeros are nil. So this will not be a part of root locus. Now what about the second part? That is the part from 1 to 2. Here we see that total number of poles and zeros are 1 in number, because only one pole exists right to this, the second part. So right to second part, total number of poles and zeros are in odd number. So this part is a part of root locus. What about third part? What are the total number of poles and zeros right to this part? So total number of poles and zeros 1, 2, 3 and 4. So total number of poles and zeros right to this third part is 4, and that is an even number. So this part will not be a part of root locus. What about the last part, that is from 0 to minus infinity? Here we see, here we again count the total number of poles and zeros. So total number of poles and zeros are 1, 2, 3, 4 and 5. So this is also an odd number. So here we see this part will also exist as the part of root locus. So I have hashed these two parts, one from 1 to 2 and another from 0 to minus infinity, as a part, as also a part of root locus. I have hashed it from blue color. Now the other next rule is about breakaway point. Now what is breakaway point? Actually, when two or more branches of root locus meet at a point and separate after meeting to that point, then that point is called breakaway point. What does it mean? Actually, it often occurs that two or more branches meet at a point. So that point is not the destination, or you can say termination point of root locus, because root locus always terminate either at open loop zeros or at infinity. So root locus has to depart after meeting to that point. Root locus has to depart from that point after meeting at that point. So that point is called breakaway point, and that breakaway point is given by dk by ds equal to 0, where k is nothing but open loop gain. Now how to determine this k? Let us take the general case of open loop transfer function. Here I have taken a particular case. So here I have generalized the case gs into hs equal to k multiplied by s minus z1 multiplied by s minus z2 dot 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 up to s minus zn divided by s minus p1 multiplied by s minus p2 dot 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 s minus pn. So this is the general case of open loop transfer function. As we know, the characteristic equation is given by 1 plus gs into hs equal to 0. That means gs into hs equal to minus 1. This is from characteristic equation. So from here we can find the value of k as k equal to minus s minus p1 multiplied by s minus p2 dot 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 s minus pn divided by s minus z1 s minus z2 dot 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 up to s minus zn. So in this way we can find the value of k. Now if we differentiate that dk, that k by s, and put that differentiation equal to 0, that will give the breakaway point. This gives the breakaway point. But here we have to note one more thing. All the points given by this equation are not the breakaway point. Only those points which satisfy angle criteria. What is angle criteria? I have elaborated that thing in previous lecture. So what is angle criteria? Angle criteria is odd multiple of 180 degree. So only that point which satisfy the angle criteria, this is the angle criteria. This is the angle criteria. So only those points which satisfy the angle criteria, that is angle PS equal to odd multiple of 180 degree, are breakaway point. So whatever point we get, we have to test whether those points are satisfying the angle criteria or not, because satisfaction of angle criteria means that point is on root locus, and dissatisfaction of this angle criteria means that point doesn't lie on root locus. So if that point doesn't lie on the root locus, then there is no meaning of that point is a breakaway point, because breakaway point is always a point of root locus. So this is the sixth point, or you can say today's second point. Now let me wipe out first. Seventh point, point number 7. Angle of arrival and angle of departure. So what is angle of departure? What is angle of departure? Actually, root locus, branches of root locus originate from open loop poles and terminate at open loop zeros. So, along which direction they should originate? Along the direction in which they originate, that is called angle of departure. Means angle of departure of root locus, and the direction along which they reach on the open loop zeros is called angle of arrival. So angle of departure is nothing but the direction along which a branch of root locus originate from the open loop poles. Actually, one more point was in the previous point, breakaway point. If R branches, let me write here, you should note this point. If R branches of root locus meet at a point, then they break away at an angle plus minus 180 degree by R. If you write this, if R branches of root locus meet at a point then they break away at angle plus minus 180 degree by R. You should note this thing. Actually, this escaped from my mind at that point. So you write this, or you must understand this point also. Now I come to the point, angle of departure. So angle of departure is nothing but the direction along which a branch of root locus originates from the open loop poles, and it is given by phi why p? Because angle of departure will always exist at poles, and that is equal to phi p equal to 180 degree plus phi. So here the angle of departure at a particular pole is given by 180 degree plus phi, where phi is the net angle contribution due to other poles and zeros at that pole. What is this phi? This phi is net angle contribution due to other poles and zero at that pole. Similarly, what is the angle of departure? Sorry, angle of arrival, because I have explained already angle of departure. Angle of arrival. So angle of arrival is just opposite to angle of departure. As angle of departure is for origination of root locus, then angle of departure for termination of root locus. And where the root locus terminate? Root locus terminated open loop poles. So the direction along which a branch of root locus terminate at zero, at open loop zero, is called angle of arrival. So what is angle of arrival? The direction along which a branch of root locus terminate so the direction along which a branch of root locus terminate at open loop zero is called, let me wipe out this, is called angle of arrival. As angle of arrival occurs at different zeros, so we denote angle of arrival by phi z, and this phi z is equal to 180 degree minus phi, where phi is nothing but the net angle. Here phi and this phi both are same thing. Here phi is also net angle contribution on that. Here in a state of pole this is zero. So this phi is net angle contribution at that zero, that particular zero, where we are determining the angle of arrival due to other poles and zeros. So what is this phi? So this phi is nothing but net angle contribution due to other poles and zeros net angle contribution at that zero due to other poles and zeros. Or you can write net angle contribution due to other poles and zeros at that zero. At that zero, where we are determining the angle of departure. So let us take the same example what we were taking, that open loop GS into HS equal to K multiplied by S minus 1 divided by S into S minus 2 S minus 1 plus J1 S minus 1 minus J1. Here how we can calculate phi? So here it is 0, 1, 2, minus 1, sorry 1, minus 1. Here it is pole, here it is 0, pole. Suppose I want to find the angle phi, this phi, at this pole, at this pole, at this pole. Suppose I want to find the angle phi at this pole. So how we can find? So actually I have to meet this pole by other poles and zeros. This is 1. Now how to calculate phi? Phi is what? Phi is net angle contribution due to other poles and zeros at that pole in this case, and in this case and that zero. So phi is calculated by here one thing I should mention in bracket. This phi net angle contribution at that pole due to all zeros minus net angle contribution due to all poles. This is sigma or summation of angle contribution, or let me write it here. Phi is angle, here this phi is this angle summation of angle due to zeros minus summation of angle due to poles. We should write this thing. And this applies for this pi as well as this pi also. So at this pole I have to find out the value of phi. So how we can find? So angle contribution due to this pole at that pole is consider this one. Again, angle contribution due to this zero at that pole is equal to this one. Here the angle contribution is this one. Here this one. Now phi, what will be the value of phi? Phi at this pole, phi equal to summation of angle due to all zeros. So there is only one zero, and angle contribution due to this zero is 90 degree. So this is 90 degree minus summation of angle contribution due to other poles at this very pole. So what is the angle contribution due to this pole at that pole? This is 135 degree, this is 90 degree, and this is 45 degree. So here we can write 135 degree due to pole at 2, 90 degree due to pole at -1 minus J1, and 45 degree due to pole at 0. So this phi will be equal to 180 minus 180 degree. So if we want to calculate phi p at what you can say phi p at -1 plus J1, then what will be the value of phi p? Phi p equal to 180 degree plus phi. And what is this phi? -180 degree. So 180 degree minus 180 degree, 0. That means the branch of root locus will originate from this zero in which direction? In direction, in this direction, x80 degree direction. This is the means in this direction, in x80 degree, in 0 degree, sorry, in 0 degree direction, means parallel to real axis. This is your real axis, and this one is imaginary axis. So similarly, if there is case of if we want to find out the angle of arrival, then instead of putting plus phi, we put minus phi, and we can find the value of angle of arrival. So I think it is clear to all of you, and this is the end of point number 7. Angle of departure and angle of arrival. So next point is point number 8. Suppose root locus cut the real axis. Suppose root locus cuts the real axis. Sorry, imaginary axis. And we have to determine the point where it cut. The value of k at that point, the value of the point. So we can determine that point by applying the Raoult's criteria, because if a particular root locus cuts the imaginary axis at k equal to some value, then if we increase the value of k, then the root locus will shift in positive half of his plane, and then the system becomes unstable for that value of k. So it is very important to find at what value of k root locus cuts the imaginary axis. So the intersection of root locus with j omega axis, or you can say imaginary axis, can be find out by applying Raoult's stability criteria. The intersection of root locus on j omega axis, this axis is also called imaginary axis, can be found out by applying Raoult's stability criteria. Another way is to determine the point of intersection is actually, as we know, GS into HS equal to -1. This is the equation this is the characteristic equation. So as we know, the value of GS multiplied by HS is -1, and if root locus is cutting at some value of k, so here this point is here, this point can be written as S equal to j omega, only j omega, because at imaginary axis there is no real part. So if we put S equal to j omega, if we put S equal to j omega in this equation, so if we put S equal to j omega in GS multiplied by HS and put the imaginary part, mind it, and put the real part, the imaginary part, because there is no imaginary, this value is equal to -1 and imaginary value is equal to 0. So if we put s equal to j omega, and then we put imaginary part equal to 0, then we can also find the value of omega. Omega means this point. So another method is put s equal to j omega in gs multiplied by hs, and then put imaginary part of gs into hs as 0. That is, Im gj omega sj omega equal to 0, and by equating this equal to 0 we can find out the value of omega. We can directly find out the value of omega. That is the point of intersection. So the point of intersection of root locus can we find out by applying Raoult's stability criteria or either by this method. Now the next point is now the next point is, that is 9th point. Suppose at some point on root locus we want to find the value of open loop gain k. Then how we can find out? Actually, I have told earlier that k is equal to nothing but the multiple of s minus p I, where I equal to 1 to n divided by j equal to 1 to m s minus zj. Now we can calculate the value of k at any point s by this relation. So what is this? Suppose we want to find out, suppose there are some poles like that and this is 0, and we want to find out here what is the value of k. K equal to what here? So what we do? This is s minus p. Suppose s minus p1, s minus p2. This is s minus z1. So s minus pi is nothing but the distance of poles from that very point, and s minus zj is nothing but distance of that very point from zeros. So we can find out the magnitude of poles by magnitude of k by multiplying the distance of that point from other poles divided by multiplication of the distance of that point from other zeros, means multiplication of distance from poles to that point divided by multiplication of distances from zeros to that point. In this way, we can find the magnitude of k. So we can find out the value of open loop gain k at any point S. So this is all about the brief introduction, or you can say brief theory of root locus. In next class, we will discuss different problems of which are asked in GATE. Thank you.